Hello, how's it going? I just recorded this whole video not realizing that my microphone was switched off, so re-recording it now. The topic of today's video is transformations and how we can set up transformations using matrices as well as an example. So to start with, a bit of the basic language around transformations. Transformations are usually done with matrices, where a matrix is an array of numbers, coefficients. Now the way you use this is you multiply a matrix with a vector to produce a transformed vector. Now the language we use here is the original vector that we put in is called the object, and the resultant vector that comes from the matrix transformation is called the image. The way this works in video games is you store information about some points, and you don't graph the points, you actually transform the points a bunch of times, and then the result of all those transformations, that is the data which gets drawn. Okay, so in practice we can make up our own transformation matrices. All we need to do is analyze what would happen to the basis vectors I and j under our proposed transformation. So I've got this graph here. I is the pure x direction vector, so 1 in the x direction, 0 in the y direction, and j is the pure y direction, 0 in the x, 1 in the y direction. Okay, so let's say we want to apply a rotation, so we pick up these basis vectors and spin them around by an angle of theta. By default, rotation always goes anti-clockwise. Okay, so imagine picking this vector up and spinning it around. Now we need to decompose that into its horizontal and vertical components in order to find the transformed vector. Using trigonometry, we can see this splits into a right angled triangle. The vertical component, the horizontal component is cos, vertical component is sine. Awesome. Now the tricky one is if we look at transforming the j vector. So imagine taking this vector, spinning it around. Because it's set up against the y-axis, it spins off the y-axis. And so this side here is vertical, but it's actually adjacent to the angle of rotation, which means that we actually have things set up a slightly different way. Now, if we look at the horizontal component of this triangle, it's sine, right? Because that's in the x direction, but that is not positive sine, it's pointing, it's just a length, right? And it's pointing in the negative x direction. So we put that in, negative sine theta is the horizontal component of this vector. And similarly, cosine theta is the vertical component of the transformed vector. So then what we do is we take the images of I and j under the transformation, compose them together, and that makes the matrix for the transformation. Alrighty, here it is. So the reason I went through this, right, and then we would use this in the normal way to give a formula for transformations of points. Now the reason I went through this, besides the fact that it's just fun, is when people see this rotation matrix for the first time, it can be a bit weird. Weird to understand, right? Cosine, sine, that makes sense. What? And also weird to remember. So just remember, you can decompose any transformation by looking at basis vectors, and that's it. So let's have a quick look. Or let's have a look at this in action. Okay, hello. So remember, in the previous video, we had the stages of transformations, and we were just moving around. Well, we can do this again, and we can see the rotation in action as well. Righty, so remember, world coordinates is just the standard kind of coordinate set. View coordinates is setting the player so they are the center of the world. So see, we're now using rotations to spin the world around the player. So the basic philosophy here is whichever way the player spins, just keep them facing the same way and spin the world the opposite direction. So here I'm going to spin the player to the right. We can see in world coordinates they've spun to the right, but in view coordinates the world has actually spun to the left. Okay, so I'll make this even clearer. They walk towards the green wall, yep, and they spin, and the world spins the opposite way. This has the effect of, well, it has the effect of already making things pretty fun. So let's have just a quick dive into the code. And I know that my last video was so comprehensible in fact that I'm going to redo my explanation, or at least go over it in some more detail. Okay, so we import Pygame. That has all of the input handling stuff that we need. We initialize it. Okay, great. We import math because we're going to be doing a bit of rotation stuff, so we'll need sine, cosine, and we'll need to be able to convert things to radians. This function here creates a screen, and I've defined its width and height. Yeah, as you can see, there are some colors here. Okay, now we're going to create three surfaces: the model coordinates, view, and projection. We're not using projection yet. The syntax here is we say pygame.surface, that creates a new surface, and these arguments are the width and height of the surfaces. So each of these three surfaces are 300 pixels by 300 pixels. No particular reason for that, I just picked it. Okay, now we need a rectangle to represent where the screen sits in the window. And the syntax here is we have the left x coordinate of the left point, y coordinate of the upper point. So you define the upper left point, and then the width and the height. Let me just kind of run this and demonstrate. Okay, so you're probably used to saying, okay, 0, 0 is down here, and then as y increases, we're going up, and as x increases, we're going to the right. Pygame does the opposite of this, kind of. So on the screen space, 0, 0 is the top left, and then as y increases, it drops down, and as x increases, it runs to the right. When we get into OpenGL, it uses the normal way where y goes up, but right now we're going to work with this. So if we look at model rect, that is the world coordinates box. That starts up here, and it's 300 by 300. And you can see how this marries up with the view rect and projection rect as well. Okay, no problem. So we've got some font stuff, and we don't need to worry a lot about the font stuff at the moment. This will all be on GitHub. You can check it out. Okay, right, so this function translate, we talked about this in the last video. It just adds a fixed amount to the x and y coordinate, no problem. This is a new one, rotate point. So what we're doing is we need to get the object data. So we need to get the original point, and then we need to apply transformation. Now, if you check, let me just bring this up. Okay, apologies about that. This should do it. Not secure. That's no good. Okay, so where was I? It says here the formula for the new x point should be x times cos plus y times sine. And that's what we got, x times cos plus y times sine. And then it should be y times cos plus x times sine. We've got negative y times, sorry, yeah, x times sine, negative x times sine, yep, negative x times sine, plus y times cos. Okay, yep. I seem to remember that because the coordinate system was shifted, I did like a shifted version of rotation, but this works. And when we look at, yeah, right. So I'm just checking this now. So if we look at my previous explanation of the rotation matrix, it should actually be something like this, right? Negative y times sine. But the reason I'm going with positive is because the y values are kind of opposite to the way a sane person would use them, right? So we just have to tweak some of that a little bit to make it look proper. Okay, I'll try to keep the rambling to a minimum. Oh, right. Ha ha ha. Okay, so go through the classes. What do we have? We have a sprite. It has, yeah, radius, and we're using that radius to generate a circle and a line, and then we're kind of drawing that onto the original image. So this original image is a Pygame surface, which is just like a big array that stores pixel values of things that we can draw. So each value will be, you know, a color. So what we can do is we can allocate this storage space and then draw to the storage space, and then later on, because this is inheriting from the Pygame, too much coffee, because this is inheriting from the Pygame sprite class, it has its own draw function which just takes self.image and draws it automatically. So this is like kind of like pre-doing our drawing. Okay, so what was I saying? We don't draw the original image, we have a copy of the image, and that copy goes through some transformations, and that's the thing that gets drawn. Otherwise, if we're rotating the player, if the player has a direction, say 5 degrees, then every frame we want to rotate it from 0 degrees to 5 degrees. We don't want to keep rotating the same original image because it will keep spinning. That's not good. Okay, so the usual stuff, right? So inputs, this function Pygame key get pressed returns the state of the keyboard. So it's a bunch of Boolean variables, and we can just test that. So when we say if key state Pygame key left, that is saying if the left key is down. And similarly for all of these other ones. Yeah, so just the normal sort of stuff. So if to turn to the left, that is anti-clockwise, we increase the direction. If we're above 360, just take away 360. That just makes sure that our direction doesn't keep going up above 360 degrees. It doesn't have to. And yeah, okay. Right. Same for going right. Now, going up or down, right? So if we go up, then we move forwards based on our current direction. If we go down, we're going backwards based on our current direction. And if we compare the forwards dx dy to the backwards dx dy, I just took negative, right? So multiplying this dx and dy by -1 will reverse its direction. Okay, so let's have a look at this. Dx is our speed, how far we're moving, times the cosine of our direction. That gives you the horizontal direction that you should move in based on your, sorry, the horizontal amount that you should move in based on your direction. We just have to convert it to radians because Python's cosine function expects an angle in radians. And when we move on to more advanced math libraries, they all expect radians anyway. So just don't let yourself be too spooked by this radians thing. Okay, and then we go through the normal stack of transformations. So model to world, what do we need to do? Well, it's already the player is pretty much already at the position they need to be in the world coordinates. We just need to spin them around. So we take the original image, rotate that image. And what this does is it takes the image data and makes a new surface, a new set of pixels that represent the rotated image. And then we need to center it around our position. Okay, all good. Okay, model to view. All we're doing is, remember, by default, just run this, by default we are rotated 90 degrees, so we're pointing up, even though right now we're looking at an angle of 0. Okay, again, I just like that. Okay, now for the wall, it's this, nothing too crazy. So we're defining a wall by a position A and a position B. That's 2 points in space, and it has a color. Okay, so if we were to set up a surface to represent the graphic of the wall, then we can't just draw a line. We need kind of a box that we're going to draw the line within. So we need to know, like, what's the width and height of the wall. So if we have a horizontal wall, then it will have a width of just the difference between its x coordinates, but we want to set that to at least 1, right? So if it's a completely this would be the vertical case where we get 1, right? So if you have vertical, then x minus x would be 0. That would be making a wall with no width. We wouldn't actually be able to draw onto that surface because it would have no width. So we just say if it's less than 1, give it a width of 1. Okay, great. And similarly for height, now we need a left and a top. So whichever x coordinate is smaller, set that as the left x coordinate. And yeah, don't stress too much about this because it works, but it's not ideal anyway. Okay, great. Yeah, so update, that's fine. World to view, this is the interesting part. So again, we shift the 2 points of the wall around the camera. So take away the camera's position and then rotate them. So don't be too scared about this 90, right? I'm going to take the 90 away and run the game. And it still kind of works. Kind of, right? So when the camera spins left, the world spins right. That's good. When the camera spins right, the world spins left. That is all that the negative player direction is doing. It's setting that up. Now, if I go back to the camera and I say, don't rotate to 90 degrees, rotate to 0 degrees, because that works, then it pretty much still works. The only difference is instead of the camera by default, here by default looking up, now by default it's looking at an angle of 0 degrees, which is fine. This is acceptable, but I don't like it. So I'm going to change that back. Yeah, so again, this 90 degrees just sets everything so that up is the default direction, and then this minus player direction just makes the world spin the opposite way to the player. And there was something else I should mention. So here I say view surface blit, and the way this works is we start with the surface that we're blitting to, then we call the blit function. Blit just copy pastes an array of pixels onto another array of pixels. It's just like drawing onto a surface. So we need a reference to the data that we're going to blit, which is a smaller surface. It doesn't have to be smaller. In this case, I'm going to be copying my rotated image onto that surface. And we need to know where on the target surface will we be blitting. So remember, a rectangle defines a top left and a width and a height. So this is all the information we need to define the little box on the screen where we're going to be pasting the player or anything else that we want to draw. Okay. And yeah, this is acceptable. So what do? We spin, so we call this rotate point. We pass in the original point, or not the original point, this is the point after transformation. That's okay. So yeah, we pass in the angle and that rotates it around. And then we just want to round those values. Okay, so it's not strictly necessary. It can actually, Pygame can handle it without rounding, but it sometimes gives you an error message, which is annoying. So we just, it doesn't hurt too much. Okay, but then what's the other thing we need to do? We need to translate these points to the point 150, 150. So if I don't do that, rotation works around the origin. So something which should be at the center of the screen, if we're rotating around the center of the screen, then first we move it. We move it so that the center of the screen counts as the point 0, 0, and then we draw. Hopefully this works. Okay, cool. So you can see that the center of the screen is actually kind of here. So it looks like all of the walls kind of work, but they've just been shifted up a little bit, right? So for example, a positive X value will be here somewhere, but if it's at the center of the screen, then everything's been shifted, so it's going to be like off screen somewhere. So that is the reason that we need to do this. And there we go. So there it is. It works. We can walk around. It's fun. Like I said, it's already getting quite enjoyable. Okay, so that will be it for today's update. Have fun. And that's it. Bye.